We are very happy to have you here this evening, Frédérik. And the title of his talk this evening is Dynamics of Old Growth Temperate Forest in Western Quebec, Understanding the Past for Meeting the Challenges of the Future. Please join me in welcoming Frédérik.
Thank you. Yeah, for today, I won't be talking about modeling much. It will be very field empirical data, so I guess that will be more interesting for you. First time that Peter asked me to come here, I thought it would be a great idea to be in Nova Scotia in the fall because it's beautiful. It would be a great idea to join these guys that I haven't seen for a long time. But also, it was a good time for me because I have 2 PhD students that were finishing their thesis on old growth forests. So I have fresh, new, hot from the oven data that I'll be presenting tonight for you. So these 2 guys are my 2 students, Jean-François Sénécal and Tiffen Debert. So Tiffen was working in Témiscamingue, in the far west Quebec, and he was working in an ecological reserve called Lac Malakizis. And there's yellow birch of 1 meter 35 and white pine of 1 meter 40 something. So all in 1 hectares, you have all these big trees. So it's very, very impressive. And Jean-François was working in Lac La Blanche Ecological Reserve, which is a forest that has this type of old growth forest. So the outline of my presentation today, I will be talking about why it's important to study old growth forests. And I get right to the most important process that is happening in that forest, which is the gap dynamics, which is most of what we have studied with these 2 theses. So the first one, old growth forest in Témiscamingue, we'll look at how this forest looks in terms of the difference between the diameter and the age distribution, and also the spatial distribution of the tree, how it works. And then we'll be looking at the second one, and in the second study that I'm presenting, we'll be comparing old growth with managed forests, which is very important if we want to address the question of ecosystem management. And for that part, I will be using LiDAR data. So we'll look at the canopy processes that are happening in old growth forests and compare that to managed forests, and also look at some spatial analysis and gap size distribution. And finally, I'll talk about the future of old growth. Is there a future of old growth? So why studying old growth? First of all, because it's a biodiversity reservoir, very important for wildlife. And the issue of the spotted owl on the west coast has been probably driving most of the energy that is still on when we're talking about old growth. On the east coast, on the east side of the continent, the pine marten also, like in Newfoundland or different places, the pine marten has been like a econestic species. But out of that, there's other critters that are very specific to old growth. Fungi, for example. There's a suite, assemblages of fungi that gather only on those type of forests. The lichen is related to time. Time is a variable for lichen development. It takes a lot of time. So old growth and lichens are intricately very associated. And lately there's more studies that have been looking at bacteria in the soil, and they're finding that the bacterial assemblages are different in old growth forests. So all these make these forests very distinct, but they're distinct also in terms of the way they provide ecosystem services. And one big challenge related to climate change is how the forest will be contributing as a carbon sink. And in the beginning, there was kind of like an urban rumor saying that old growth, they're neutral carbon speaking. And research that have been done since the 2000s are showing that the old-growth forests are accumulating carbon as fast as young forest. And it's all accumulated in the soil. For that, like I'm talking about Quebec. In Quebec, we have a new Forest Act since 2013. And the base of the new Forest Act is ecosystem management. That's the paradigm that drives the new Forest Act here. And ecosystem management is based on the functioning of the forest, natural functioning, understanding how the natural forest is work. So understanding that means understanding also exceptional cases. How often are they, those old-growth forests? So the old-growth are witnesses of the functioning of the forest. And there's many cases where we have tracts of the forest at the beginning of the 19th century or even before. We know that there was much more than what it is right now. It's a rarity in the landscape. So that is a reason to understand how it works. For example, here is what is understood to be the original growth forest in the island Victoria and the portion of British Columbia south. And now there's only 10% left. So those kind of difference drive also the way that the society look at how we manage forests. And we have also spiritual value related to old growth. This is the bear spirit on the Victoria Island that has been shot by a photograph. And those spiritual value are important for many communities. And finally, they're fun, they're cool, they're impressive, they're beautiful. That's a good reason to study them, no? Don't you think? And this is a tree that my mom is standing by. This is a LRC. LRC is kind of a tree like the sequoia. So this tree is estimated to be 4,000 years old. There's soil developing on its branches, and there's tree growing on the soil that is developing on its branches. Can you imagine? It looks like the movie Avatar. So that's very impressive. All of that make them very interesting to be studied. But what interests me most is how it works, how that forest works, like how the gap regimes work in these forests. Now, we know that those forests have been escaped from catastrophic disturbances for centuries. That's why they are old growth. And they have developed their own endogenic systems of disturbance, which is the gap phase dynamics. So the gap phase dynamics is about 1% disturbance rate per year, and it's small gaps, very small gaps. So we have disturbance rate between 0.5 to 2.2% per year. So it can be very varying. You see that for ecosystem management, if you use the 0.5 or you use the 2.2, it's almost 5 times more. So if you use that for ecosystem management, it's important to understand how it works, really. And the way that gaps are done are very important. There's many mechanisms that make gaps, like trees are snapped. And when they fall, they crush other trees, make like sub-canopy gap. Some trees are dying standing, like that, this one, but they're doing that slowly. They're not doing that suddenly, like when we harvest a tree. Some are bending, so is it a gap or is it not? But it's changing the canopy and the light regime for sure. And most of the time, it's only branches that are falling, like this yellow birch. No, that's a maple. Yeah, but yellow birch does that. They have a very large crown with large branch systems that falls and make a gap. It's not a tree that makes a gap, it's a part of the tree. So I'm getting right into the science now. The first study is this old-growth forest in Témiscamingue. And the particularity of that forest is that it's northern limit distribution. And we were asking would it behave like what is known for this kind of forest at the center of its distribution? So we look at the diversity, the DBH and the age structure, look at how live and dead tree will be spatially organized in those forests. Also, we don't see that, but with the dendrochronological analysis, could we reconstruct what is the gap dynamics of that forest? So this is a paper that has been, this is a paper that has been published in Forest Science. So this is where it is. And what is important to understand is, it is that it's very limited of the deciduous temperate forest in North America. So we have that forest zones there. So what we did there, we sampled old growth deciduous forest where there was no trace of logging, presence of old growth of dead wood, and kind of something looking like an uneven age distribution, like this one. And it has to be in the sugar maple yellow birch domain, so those three has to be dominating. So we have large sample plots, a quarter-hectare sample plots, and we measured and located all the trees, living and dead trees that were in those plots, and we core them in order to do the dendrochronological analysis. So we made statistical tests for comparing the DBH distribution and the age distribution, and we did spatial analysis using point pattern, market point pattern. So we have like a map of tree like that with the size of those trees. And then we could look at how, with point pattern analysis, they are organized in space. So first of all, one of the hypotheses we had, and this was coming from what we are seeing in the center of distribution of the deciduous temperate forest, it usually increases in species richness with stand age. So what we have here as an indicator of age of the stand is not the oldest tree, but the 98th percentile of the age of the community of the trees that is there. So we have different species, but most of them are dominated by sugar maple and yellow birch. And there's a balsam fir that is often observed in these stands. But one thing that we observe is, instead of increasing the diversity, it's decreasing with stand age. Thank you. So, dead trees. We found that 28% of the dead that we sampled were dead trees. That's quite a lot. That's quite a lot. And this is all the sample plot. SP stand for sample. And we have the number of trees living and dead. We look at the spatial distribution between the dead trees and the sapling, and there was no relationship. And that was surprising. We expect to see like a spatial relationship with the sapling. Those are the DBH distribution. We try to fit different type of distribution that we see on the right bottom. And most of the time it was exponential, negative exponential, or a 2 or 3 parameter variable. But what was interesting is when we look at the age structure using the dendrochronological analysis, we had age structure that was not related to the DBH. Some had continuous recruitment, some others had pulse of recruitment, but whatever was the recruitment type, we end up with a negative exponential distribution. So there's kind of a, what we call a strange attractor thing, that whatever is the initial history of the way that the stand is developing, it tends to converge into that kind of distribution, DBH distribution. For the spatial structure of the living trees, we found that species speaking, age speaking, or DBH speaking, there was no spatial structure. It's all random. Unless for that little portion for DBH, when we put all the plot together, we increased the statistical power, and we saw that was repulsion for dBH in that zone, which means that trees will tend to be apart at some distance more than randomly, which makes sense because of the crown size that will repel the establishments for the sapling. So this all suggests that gaps happen randomly that are small, and it looks like this forest is acting like other forests at the middle of the range of its distribution. So for the second part, we reconstruct gap dynamics using the dendrochronology, and we're wondering what kind of disturbance rate we will be finding with that. So remember, disturbance rate range between 0.5 and 2, but the average is 1% per year. We're expecting to have like a higher disturbance rate because we're at the northern distribution, there's more chance of having climatic accidents or mortality. And we were expecting, because of that, to have like a gap size distribution that would be skewed to the right, meaning that there's more bigger gaps than what we observe usually in the center of its distribution. So we identify gap using dendrochronology. We split in 20 years period. We use the boundary line release criterion, which compared the growth by 10-year steps and try to find change in growth. So we had a major release, it was over 50% of change in growth, a moderate release with 20 to 50, and we did that to identify the extended gap. Extended gap means that is tree to the tree. So that also helped us to figure out what would be the disturbance event. So we figure out with this where the change in distribution, and they were related to the recruitment period. So the pools that I was showing previously were related to the disturbance event that we found with the dendrochronology. So to reconstruct the gap, the way that we were working, when we had a major release, we were thinking that we were at the center of the gap. When we had a moderate release, we were at the edge of the gap. And with the location of the tree, without release, we could make up like a patch gap, or a gap patch. So using this, we end up filling the entire plot. So we could make it and having what we call a number maximization gap, or if we take these edges and combine all together, we have what we call a size maximum gap distribution. So we use the two and compare how the result will be with that. So you have all the different plots, the element plots with the 3 periods, and those are the gap that we have reconstructed by 20 years period using dendrochronology. So remember, it's a quarter-hectare plot for each, so it's a lot of work. So that have allowed us to determine what would be the disturbance rate for the element plot. And what you see when you look at the mean by the period, we're close to the 1% per year. But we have quite a variability in these plots at the scale of those plots, from 0.36 to 2.2, which is close to what have been related in the literature that I was showing previously. So it's very interesting that in the end we have something that is very close to the literature, 100%, and the range is about the range that is collected in the literature. For the gap size, that's how it shows. Gaps are very small. 85% of the gaps are smaller than 50 square meters, with a mean of 39. So that means that most of the gaps are even not 3 crown, are less than 3 crown in terms of openings. Here we have done some kind of analysis to understand what will be the relation between the disturbance rate that we have, like this way, the mean gap size, with the species that we have in those plots. And what we found that yellow birch and balsam fir will be related to small gap size, while sugar maple was when the disturbance rate was higher and the mean gap size. So when we interpret that using the horticulture of the species, balsam fir is a small crown, we can figure out how. Yellow birch is the one that is branch shedding, so it makes small gaps, while sugar maple is a snapping tree, so it makes bigger gaps. So it's related to the ecology of the species. So conclusion, gap might result from the depth of a single branch or a tree. Gaps are small, and what we found is that our gaps in our system right here in Témiscamingue, the gap are smaller than what we observe in the center of the distribution. So basically, if we make a synthesis of what we have found with that first study, with that forest, old growth forest, it's behaving the same way that it is like 3,000 kilometers south, except that the gaps are smaller. Now I'm getting into the second study, which is using the LiDAR. So we want to compare the gap dynamics and the canopy processes for old growth deciduous forest in Outaouais using multi-temporal aerial LiDAR. Yeah. So the question we ask is how different the gap dynamics would be between old growth forest and managed forest. Now, the first objective was to compare the canopy structure and the canopy processes, to identify the mechanism associated with the canopy height reduction, to characterize the spatial relationships of the canopy processes, and to compare the gap size distribution also, but now using LiDAR instead of using the system that we did in the first study. So why using LiDAR to study gap dynamics? First of all, gaps, it's a very difficult process to capture at the landscape scale because it is fine-grained, it is diffused, it's continuously generated and changing. And with LiDAR, by capturing the 3D signature of the canopy, we're able to get into this changing in the spatial structure of the canopy to analyze that. So we hypothesize that the past disturbances are imprinting into the canopy at the landscape scale with long-lasting feature in terms of 3D organization of the crown. And with that, we can characterize the forest coming from different disturbance regime, meaning old growth forest has its own regime and managed forests have their own regime. So the study has been done, you see Quebec, we're in Outaouais, and I live right there. Ripon is where my institute is. So we're close to Ottawa, about 50 minutes to Ottawa. So it's a very nice place, it's beautiful. And our institute is a very great place to work. I'm quite happy about it. I'm happy because that institute happened because of me and a friend of mine. We started it, so I'm very glad. We use 11 square kilometers landscape to compare the structure with the LiDAR. And we have multi-temporal aerial LiDAR. So the first set of data is coming in 2007. With that, we had also the disturbance history of each landscape using the Ferris inventory, the past aerial photos, and we had also 3 1/4 hectare plots per landscape. So 33 for the entire 11 landscapes. So if you look, we're in the sugar maple basswood and sugar maple yellow birch. We have 3 old-growth forests, 2 selection cut. One is old of 15 years and the other one is 4 years old. We have some that have been diameter limit cut with 2 pass. Some came from fire in 1925 and there was diameter limit cut after that. So, oh yeah, there's some other that have been a mix of selection cut, diameter limit cut, and one that came from a 100 years clear cut, and this is in the Gatineau Park. So they're thinking that's an old growth forest, but 100 years ago it was a field. And the second pass, it was in 2013. It wasn't exactly the same forest that we have sampled, but the old growth forests have been the same. And the selection cut forests have been the same. And we added some other selection cut that were already the pass of 2007. So we have the LiDAR. We make up the canopy height model using the LiDAR. We mask the openings to be really in the forest systems. And we make the gap delineation, so all those little red dots are gaps that have been detected using like a gap detection algorithm. I'll talk about it later on. So to make the canopy height model, we have the surface model and the terrain model. So we subtract the terrain from the surface and we get the canopy height model. So that allowed to have the canopy height distribution for each of the forest landscape. It's very interesting now we get that for 1 square kilometer entirely in one shot. So when we compare old growth forests with selection cut forests, first thing that we see is the shape for the young selection cut is very different from the old growth forest, while the 15 years selection cut is getting very close to the distribution of the first 2 old growth. Those ones that have been cut under diameter limit cut are more kind of distinct in terms of signature of distributions. That one is recent diameter limit cut and selection cut. We see that there's a lot of young, not young, of low height spot compared to old growth. These ones come from the fire. They look more like a monotonic kind of forest, even age, and that's the kind of signature we'll get. This one is younger because of that compared to this one. And finally, this is the one in Gatineau Park that has been coming from a clear cutting 100 years ago. It's getting closer to the old growth tree, so it makes sense why people are misinterpreting that forest. So I told you that we had an algorithm to detect gaps. We use what we call adaptive thresholding algorithm. The idea was that a gap is a change in canopy height that is steep enough to cause a break in the canopy. So it's kind of a general. But if you look now in the literature, there's many ways to detect gap using LiDAR. This one is interesting because it's adaptive according to what is happening in 1/4 hectare surrounding the pixel. So it looks at the mean height for the entire and also on taking into account the variation in height. So if the height of the pixel is smaller than this or smaller than 20% of the max height, so you get a gap. And we have gap size minimum of 4 square meters. So gap fraction, that's something that is interesting. So remember, we have those maps and we have all these little red dots that identify the gaps. So we have our 3 old growth forests, and then we have partial cut forests that are ordered by age. What is interesting is those 2 ones, the first LiDAR pass was before, it was in 2007. So what we get, the difference between the 2 is the effect of the cut. Like this one, 2007, and 2008, there's the cut. The second pass is in 2013. That's the difference in gap area in these landscapes. Okay, here is 2012. So when we look at that, like more in a general way, we see that the first 5 ones are very close together. So which means that after 13 years, we have something that is very close to old-growth forest in the selection cut. And we see also that it takes about 13 years, here it is 20 years, it takes about 13 years to stabilize and get close to what the old-growth forest. So that's an indication very precious for ecosystem management. The second work that we've done, and most of it was using the multi-temporal LiDAR. So we had the Canopy model in 2013, and we subtract the one in 2007 to get an idea of the change. So for example, here is a LiDAR image, and we have the gap in green that have been identified in 2007. Then we have the flight that has been done in 2013, and we have the gaps that are identified in 2013. And when we mix the two together, we have the portion of the gap that were already the gap that stayed. We have here the gap closure. What is surrounding the red in green is the gap closure. And what is in yellow is something that happened that doesn't qualify as a gap, but is a reduction in height. And it is what we call canopy erosion. So it's not sufficient. For example, here we have a canopy gap, and here we have a canopy erosion. That's a process, a canopy process that we have distinguished. So for example, here we have the 5 canopy process. In green, which is dominating, is the canopy growth, meaning that a tree was there, it is still there in 2013, and it had grown for a few meters. Gap closure is in blue. Gap growth means that was an old growth, and it has grown but stayed as a gap. Yellow is erosion, and red is new gap. So this is old growth 1. We have erosion here, we have new gap there. We have old gaps in gray, so meaning gap growth. And we have gap closure here, here, and here. And here is the partial cut in 2012. So this is the most recent one. We have the gaps generated by the cut. We have the erosion, and right now you can already see that there's a spatial organization between erosion and new gaps. Like the portion is surrounding the gaps. So we have canopy erosion surrounding. And we do that, and we accumulate those pixels that contribute to each of the 5 canopy process in order to understand what's going on. So right here we have the tree growth, and again we have the partial cut that are ordered by time. And here the 2 that are after the first pass of the LiDAR. And we have the 4 processes here. First thing that we see is canopy erosion for the old growth, and the 2 old partial cut are quite more important than the middle-aged partial cut. And we see also that trend of seeing the erosion being decreasing with time. When we look at the canopy gap closure, during that mid-age partial cut, that's where the gap closure is the most important. And at the same time, there's the growth in the gap, while the growth in the gap in these 5 is very low. And this is the canopy growth, and we see that there's a tendency of decrease after like a certain 18 years. So once we get that, we can look at the change in volume. how each of these processes, think of the forest being like a grape, and there's something under it that make it bumpy. And there's something that happened between one and the second drape, and they have change in shape and make the volume changing. So there will be canopy growth, canopy erosion, growth in gaps, new gap closure, and here is the balance. I mean, in the end, when you add everything that is positive, new canopy growth, growth in gap, and everything that is gap closure, this is positive, and we have the new gap and the canopy erosion that are negative. So we see how the balance of that is happening. We have old growth, the balance is the black one with the dotted line, and we see how it drops in the managed forest. So those allow to characterize the canopy processes of the not only the gap, but all the growth of the forest. And we can check how effective like forest management it is in making a forest growing. And it's surprising to me to see that those forests don't grow that much more than the old growth forests. We would have expected that it would be. And this is a message to send to the manager. You can have forests that are older and are still accumulating space of canopy. And when you think that the photosynthetic systems is getting bigger, usually you think that you're getting more wood too.
So you're measuring total volume there?
Total volume of the canopy. As I was saying, think as a grape. Okay, now we were interested in which mechanism will be associated with these processes. We have stand-dying trees, snap, uprooting, partial branch, and tree bending. And the question that we had is, which of these mechanisms is creating what in the processes? So we went back in those forests and we made sample plots of 100 meter by 100 meter in new gaps and erosion patches. We had in the beginning 101 patches, but 25 patches has to be discarded. And there was 5 patches that we could not figure out what kind of mechanism was inside of that. So we end up with 71 patches that were left for the analysis. And we found that there was 1.1 dead tree per patches. So it helps for talking about forest management. What kind of systems make that? And 0.93 damage tree per patch. So this is a patch where there's a change in reduction in height. We have erosion, we have new gap, old gap. What we found is the pre-existing structure was quite determining what was happening. And we found that paper from Parker 1995, he's talking about sub-canopy gap. And it's saying that the gap that looks like a well, which is the classical thinking or view of what is a gap, is very rare. And it is because you have all these sub-canopy systems in terms of structure that can generate different things. And if you think of these different structures, only these sub-canopy gap structure can generate something that will lead to a well-like gap. So he measured that and he found that only 23% of the cases were leading to well-like gap. So we were wondering, those processes, are they derived from what's happening with the tree, or are they happening or because of the pre-existing structure that was there, the sub-canopy gap? So we made a model. First of all, we found that all these mechanisms were not all the same. Surprisingly, the uprooting was very low in our system. The branches was very important, and the stand dying tree was very important. And you know what? Why? We're getting there, the beach bark disease. It just came in during the study that we did. And a lot of the huge beaches that we had there were making those kind of stand dying trees. Another thing that was surprising is those bent trees are not uncommon. They're very common. A quarter of time, that's what creates a change in the height. This is not a gap. And this is particularly important after the ice storm that we had in 1998. And we still see that. We have, like with climate change, more of these spring hot with a very big load of snow, wet snow. And when we come back in the summer, we see those kind of clump of trees that are bent like that. So this is a process that hasn't been very documented in terms of canopy change process. So we use model selections, and that's model 2 that have been selected. And surprisingly, none of the mechanism was selected in the model. Only the variable that was showing the adjacency with old gap, the mean height of the spot in 2007, and the patch size. So when we look at the coefficient, it means the closer you are to an old gap, the more likely you are to be a new gap. The lower was the spot before in 2007, the higher is the chance of being like a height reduction, which is surprising. We would have expected the inverse. And the greater is the patch size, the more chance is to be related to a new gap. Okay, so we have new gap erosion. How are they organized in space? So we use point pattern analysis. This time we use the one with finite size object. And we use programmative to do that. So what it does, it takes the original landscape and scramble everything. So you generate like a null model with that. You make like a zillion simulation and you get what we call a null model. So the question is, if you randomly reassemble those patches and you compare to the random reassembling of that, will it be different? That's what the test does. And see here is what the old growth, the kind of structure of the gaps. It's kind of, I would ask you, would you see any clustering or repulsing systematic distribution in this just by eye?
Okay, the left is the model and the right is the actual patch?
Yeah. Do you see a difference between the two?
No.
Yeah?
I imagine there's a difference, yes. With
Yes.
more structure in one group.
Or structure there?
Apparent.
Okay. So this is just one shot, but the null model is made of hundreds of these scrambled landscape. And then we use bivariate relationships to look at the relationship between the new gap and the erosion. So what it does, again, it doesn't scramble the thing, it just retag randomly the patches and see if you do the null landscape by retagging the type of patch, is it different from the one that you have compared to the null model. So this is the result that we got. Again, we have the old growth and we have the partial cut that are ordered by time. We have the patch type, new gap, erosion, and we have two distance, close distance and far distance. We have here for the gap against the gap and the erosion against the erosion. And for these two, we have the gap against the erosion against the gap at close distance, and the gap against erosion against the gap at far distance. So what we see in red is attraction. So it's making cluster. And in blue, it's repulsion, which means that it's more looking like a systematic distribution, like a checkerboard, for example. And what is white is random. So what we found at close distance for the old growth, gaps, new gap and erosions that are systematic. They're distributed systematically, more like a checkerboard at close distance. However, at far distance, erosions make cluster. When we have attraction, it means that we have large groups at far distance of erosions. When we look at the bivariate one, what we're looking is at close distance, gap and erosions are most of the time found close to each other. They love each other, that's what it means. What is interesting is those middle-aged partial cut have nothing, almost nothing all the way. But recent partial cut, they have the same kind of attraction at close distance. So this is a story how it is organized. We see that there's a difference between the old growth and the managed forest, but not what we were thinking or expecting. And finally, we're asking what would be the gap size distribution and how it compared between the managed and the old growth forest. The first question, which is much more theoretical, but my students like it, is a power law or a normal distribution, and is it the same for the old growth and the managed? The second question is gap size distribution for growth forests. Are they the same when you look at what it was in 2007 and the second flight of LiDAR in 2013? And the last question that we ask is, are the gap size distribution between old growth forests and managed forests similar? So when we look at the distributions, the power law was fitting well to each of the forests, whatever is the forest, although this is the power law in red. For the large gap, it was not well fit. So we had a good fit for the small and mid-sized gap up to 100 square meter. And starting there at 150 meters, there was like a deviation. So it means there's a theory about the power law, meaning that everywhere where there's a old growth forest, the gap size will follow the power law. That's not what we're finding here. The other thing is we have the log normal distribution, which is the one in black. Like the old growth forest is much closer to the log normal than the power law, but there's no statistical differences between the two. Okay, when we look at the very recent selection cutting, we see that the patches are much bigger. We get up to over 2,000 square meter patches, while the biggest was 300 square meters for the old growth. So very different shape of distribution for a recent selection cut. And when we look at a mid-age selection cut, we start to have the shape of what we get with the old growth. So we see kind of a transition, getting close to what is an old growth with time after selection cutting. So will the gap size distribution for old growth forests differ between 2007 and 2013? We use a non-parametric Wilkinson rank sum test. And what we found is yes, for 2 of the 3. They don't have the same gap size distribution, which means it's highly variable with time. And the third question, are the gap size distribution between old growth forests and managed forests similar? It's very interesting there. This is from old growth 1, and you see that it's not different from the oldest partial cutting, and at a certain point, like starting here, it's getting different. So it takes time to reach the same gap size distribution. Okay, what have we found? You know that song? Old growth forests exhibit a negative exponential deviation distribution, whatever the recruitment pattern. Live and dead tree species, size, age are randomly distributed, suggests that gaps are small and occur randomly. Gap disturbance rate vary between 0.36 to 2.27 with a mean of 0.96 per year, which is what it has been seen in the literature, but we had gaps that were much smaller than what I've seen in the literature. In the second study, we found that gaps represent between 6 to 8% of the forest area, and we did another study that I wasn't presenting here, but of this 6 to 8%, 20% of them are permanent gaps, or semi-permanent gaps, which means that are not changing because of outcrop of rocks, kind of cavity of water, they're not changing with time. Canopy erosion is a process, a canopy process that is very important, more important than new gap creation in terms of volume, but has been very poorly documented up to now. Yeah, old growth forests have more erosion and less gap closure than managed forests. And the height reduction patches from the model that we found is a combination of sub-canopy structure, mostly, and the mechanism that death or the damage tree. Something that I would like you to remember from, if there's only one thing, is this is very important. The classical well-like gaps doesn't exist.
Meaning from full canopy. Oh,
Yeah, like a well. Think more like a Swiss cheese or a fabric or a porous material. This is how the canopy behaves. This is how it is. This is how light percolate and diffuse and reach the plant in the sub-canopy. Okay, this is stuff about the distribution, but what is very important is the erosion and the new gap are very closely related. And this is the parallel thing. So it takes 16 years for the gap size distribution to look like an old growth forest. Okay, what does all that mean? Or more, I'm getting more into the management implication than the scientific implication. This is something different I won't be talking about. We often hear that selection cutting is mimicking the natural disturbance regime of the gap phase. But those two studies are showing that it's partially true, and in many cases will be far from true. The pH distribution is truncated for large trees under selection cutting. Under selection cutting, we have long rotation cycle with higher disturbance intensity. It comes with cycles. While the old growth forest doesn't work like that. There's sometimes intermediate disturbances like windthrow that comes, but it doesn't come regularly every 30 or 25 years. It comes every 300 or 500 years. Spatially, the disturbances are synchrone in large operational zones. What we found is this is not the case. Old growth doesn't work like that. And what happens in selection cut, by having that synchrone and openings in that operational zones, you have then like a rush of shrub development that make like a kind of a umbrella for light. And in many selection cut forests that have been passed 2 times, 3 times in Quebec, we're seeing what we call a recalcitrant understory, which impedes the growth and the establishment of the regeneration. So it has important ecological implications. The gap size distribution also is greater than what we're seeing under old growth for a large portion of the rotation cycles. And also the gap spatial distribution, spatially, they're not organized the same way as the old growth. Finally, the opening mechanism when we do selection cut is sudden and do not have its ecological equivalent. You think of the 5 mechanisms that I was talking about previously, the one that will be the closest is the snap tree, which was like, I don't remember exactly the percentage, but it was between 20 and 30%. So, how can we improve our practices? Surely by shortening our rotation cycles and having lower disturbance intensity, dispersing our operational zones. For sure, we need to use single tree cutting and avoid cluster. And finally, I have to talk about climate change because that's something that I'm studying for now since 2004. Sea old growth in the middle of all of that, and climate change is one of the forcing that are happening, but there's other forcing. Like here is the nitrogen depositions, and we're right here. Close to Montreal, we have 10 times the normal distribution that we should have because of the plume coming from the industrial zones in the Great Lakes. 10 times means it's 10 kilogram per hectare. It's 3 times more than the toxic level. Well, we start to have a toxic response from the plant. And something that's happening in those forests there, we start to have nitrophilous plants that are invading the understory. For sure, we have this critter that we call it the big rat in Quebec. And we have exotic that are invading the forest. This is Cathartus ramus that now is getting into the forest. And we have for sure little beasts like the one that you have here in the Halifax, which I think that's the one, huh, Peter? That's the... yeah. This guy?
I'm not an entomologist.
Looks brown.
Okay, but here we have the emerald ash borer, yeah. And I took my plane from Ottawa this morning, and all the way to the airport, it looks like it is winter because all the trees are dead, and it's very sudden. The ash trees were the before we have the elm, that was what we call the foundation species for the swampish type of sites. With Dutch elm disease, we lost that foundation species, but the black ash was the one that would be kind of taking over as a foundation species for that. But now we have the emerald ash borer that's taking the ash out of those sites, and there's no other species that can take over. So we'll have drastic changes in the forest type. So what I'm saying here is there's forcing here of global change. What will happen to our old growth forest? That's a very important question. I would advocate that silviculture could be a tool to preserve some of the old growth characteristics. We might be getting into an era where human needs to help the forest using silviculture. And this type of silviculture is called adaptation silviculture. And it's based on the paradigm of the vulnerability and adaptation, where you have a global change that brings some kind of exposition. And your system is sensitive to that, which means it generates impacts. And the importance of the impact will be depending on the exposure and the sensitivity of the systems. So high sensitivity, you don't need a lot of exposure to be impacted. And also you have the adaptive capacity of the systems. When you bring all that together, you see how vulnerable your system is. So think of old growth, how vulnerable they will be to global change. So adaptation, bring adaptation measure that will change the exposition, change the sensitivity, or increase the adaptive capacity using reinforcement measure. So I give the example, you have a pest, you spray, you lower the exposure. You have a pest, you do selective thinning, you reinforce the growth of the trees, so less sensitive. You have a pest, you fertilize, that's an adaptation to change the dynamics in the systems. So we have to think very differently now when we talk about ecosystems and managing ecosystems. We have to be very humble. There's surprises more and more. What we knew about the way ecosystems are functioning are less used, or yes, are more obsolete in many cases. We have to think of multiplying trajectories in the ecosystem development and explore the envelope in order to identify the most robust solutions that will be converging to desired state and identify, you see, the risk of irreversibility for undesired state. So, and that's something for scientists, it's very hard. There's no best prediction, and no best treatment at the best place. You have to think in terms of portfolio, and that's what Miller and Stevenson have brought in 2007. There's no single solution fits all future challenges, especially in the context of changing climates, and that's the best strategy is to mix different approaches for different situations. Using three principles: resistance, which will be limiting the change by protecting specific important value. So in the landscape, old growth are into that category. How can we improve resistance? Resilience is functional, it's related to functional diversity to promote fast ecosystem recovery. So it's once it has been hit or forced by a change, how can it bring it back? How can we bring it back fast? And this is kind of a triage approach, which is facilitations, is recognizing that that forest will change. We have nothing we can do. The only thing is, can we help the forest to change faster? And that's where adaptation in silviculture can play a role. So in the United States, they have started to have a network of sample plots where they were doing trials of adaptation. And they used that gradient from resistance to resilient to transitions to develop, to cope with the vulnerability against the global change. So for example, we can have biological invasion right here that bring a kind of a vulnerability, call it A. We have climate change. We have atmospheric pollutants, and we have pests like insects and disease that brings different type of vulnerability. Which scenario you will use? So the portfolio approach means, okay, try to develop a scenario for each of these cases using resistance, resilience, and facilitation. Look at what kind of silviculture strategy you lay out, and see if there's any convergence that's more likely to be happening. So instead of looking for the best, we have to look for the most robust. That's what I will like to leave you with. That message is we have to think of old growth forests as how we make them more robust to face those different global change. Thank you.